In this problem, we have a line charge and a sheet of charge separated by some distance, and we're looking for the point where the force on an alpha particle is 0. An alpha particle is a charged particle, and the force on a charged particle is 0 where the electric field is 0. Let's draw a picture and take a look at the situation. The line charge has some positive charge distributed over it. Our sheet of charge is negative. And so let's look at the electric field from the line charge first. Everywhere to the left, the electric field is pointing to the left from the line charge. It's a positive charge, it radiates outward. And everywhere to the right, it points to the right. We basically have three regions we're concerning ourselves with. One is the region all the way to the left, the other is the region all the way to the right, and then we're interested in the region right in the center. So we want to know, where could the electric field possibly be 0? Now let's take a look at the electric field from the sheet. The sheet's negative. So the electric field points toward the sheet. So we know that in the center region here, both electric fields point in the same direction. We'll never get 0. But there's a possibility that out here to the very right, we could have a 0 electric field, and there's a possibility over here on the left side, we could have a 0 electric field. So we're looking for the point where E equals 0. First, let's find the electric field from the line charge. So we've got some cylindrical symmetry here. Here's our line charge. I'm going to choose a Gaussian surface. That's a cylinder. Okay. And I know the integral of E dot dA over that closed Gaussian surface is equal to Qn over epsilon naught. I can break this integral up into the integral over the top of E dot dA plus the integral over the sides of E dot dA plus the integral over the bottom and that has to be Qn over epsilon naught. So let's take a look at each one. The top is going to give me 0, and the reason I get 0 is because the cosine of 90 degrees is 0. Basically, my electric field is pointing this way, and my area vector points up out of the top surface, and so I get a 90-degree angle there. Similarly with the bottom, my dA is pointing outward from my Gaussian surface, and my electric field is perpendicular to the line charge, so I get 0 for E dot dA over the bottom. And now let me take a look at the sides. This is going to be E times the integral of dA over the sides. And so I end up with E times 2 pi RH is Qn over epsilon naught. And Qn over H is my lambda. So I end up with E, it's 1 over 2 pi epsilon naught lambda over R, and I really should have a direction. I'll put radially outward, since that was a positive charge distribution, and that's a vector quantity. Okay, this is, I could put this in terms of K, but I think I'll just leave it the way it is. Now I need to look at my sheet, and for my sheet I've got electric field perpendicular to the sheet, so I need to choose a Gaussian surface where all my surfaces are either parallel or perpendicular to my electric field. That's the easiest. I could use a cylinder on its side like this, or I could put a cube or a box in there. Any of those would be fine. I'll use the cylinder, and I'm going to start off with the same Gauss's law. E dot dA over a closed surface is Q in over epsilon naught. I'm going to break this up into the integral over the left side of E dot dA plus the integral over the sides plus the integral over the right side. And that's Q in over epsilon naught. Now on the left side I end up with a negative EA because my electric field is pointing in and my area vector is pointing out, and so there's a cosine of 180 degrees there, which gives me a negative sign. For the sides I get 0 and I get a negative EA for the other side. And so I get my electric field is equal to minus 1 over 2 epsilon naught Q in over the area. And Q in over the area is my surface charge. And I'm going to get rid of my negative sign and just indicate the direction with words. I think that's a little cleaner here. E is equal to the magnitude of my surface charge density over 2 epsilon naught, and the direction is toward the sheet. Okay, so we have our two electric fields. Now we need to know when is the electric field 0. So the condition we're looking for is the electric field for the line has to be equal and opposite the electric field for the sheet. Or we can pick the region based on our drawing we did at the start of the problem. We know we're either in region to the left of both of the charge distributions or to the right of both. We can't be in between. So I'm going to get rid of my vectors and just look for the point where the magnitude of the electric fields are equal, and I can check the direction from my drawing I just had there. So my line charge, 1 over 2 pi epsilon naught lambda over r. My sheet, sigma over 2 epsilon naught, and what I end up with is r is equal to 1 over 2 pi 0.16 meters, 16 centimeters. So let's draw a quick picture here. Here's my line. Here's my sheet. And I know that they are separated by 10 centimeters. So 16, the electric field from the sheet is uniform everywhere. It doesn't fall off as you move further away, but it does fall off as you move away from the line charge. So 16 centimeters away from my line charge, I have an electric field at 0. So I come over here 16 centimeters, and I say E is equal to 0 right there. And then I go 16 centimeters on the other side. And I say E is equal to 0 right there, because those are the two regions where I could possibly have 0 electric fields. In between the two, I can't. They point in the same direction. So on the all the way to the right of the two charge distributions, I can have a 0 field, and all the way to the left of the two, we can have a 0 field.